Good evening, everyone, and welcome to this IET Sussex webinar. And my name is Mike Underhill, and it's my great pleasure to be able to introduce the speaker this evening. And by the way, you may not realize that the speaker is actually zooming in from Seattle in Washington, but more of that in a moment. So my job now is to introduce the speaker. And as I said, it's my great pleasure to introduce Dr. Mark Harper, all the way from Seattle in Washington. And I've known Mark since the year 2000, when I was lucky enough to have him as a research student, and he was working on electrically small antennas at that time. Now, after then, Mark joined Antenova and in Cambridge and became the antenna manager and invented their MDA technology, and also had lots of patents with them in there. But then in fact, his antenna designs ended up with 120 plus million antennas in laptops, etc. During that time at Antenova, he also spent some time in Japan with, I think it was Murata, training engineers, etc., all to do with this technology there. But in 2013, he moved to Microsoft in Seattle, in Washington State, as lead antenna architect, and then more recently becoming senior director of antenna design, as he is now. So with that interjection, Mark, may I hand straight over to you, and away you go.
Welcome. And it's probably a good night, not good afternoon for me, but if you're in the US, but good evening to everybody in Europe. So thank you, Mike, for introducing me. Yeah, my name's Mark. I am become the senior director of antenna design for Microsoft. My team is actually based in the Surface team. Microsoft Surface Devices and the devices org. And you can actually, if you look on the first slide here, you can see kind of a sample of some of the devices that we're involved with. And from Xbox on the left there, all the way to like Surface Hub, which is above it, which is just a big sort of display with integrated computing inside it. But so it's been quite a journey for me, coming from learning about antennas from Mike. Mike was a very good teacher, and part of my success is because of him, actually. So I'm very lucky to have somebody as good as him as a mentor through my career, and it's definitely done me wonders in terms of my career. So we are here today to kind of look at antenna design in can you see the slide? Okay, somebody's asking about full screen. I don't know how to do that. Let me see if I can do that. Sorry, let me check. Okay. I don't know what people can see.
No, it's fine, Mark. Going, okay?
Okay. Yeah. So let's crack on. Basically, I'm going to talk about we can't talk about all these devices. We just don't have the time. So what we've done is actually look at some of the devices. And I just want to go quickly into this guy. This guy is my CEO, Satya Nadella. And he's a great believer in our devices, Surface devices, and in our organ. The reason is he loves software. This guy loves software, and the only way you can really make software shine is by having it on hardware like Surface. So our devices are really there, and they're there to be designed to make our software shine. So the collaboration between software, hardware, being that silicon ecosystem, the Windows software system, we work very closely together inside Microsoft to make the embodiment of Microsoft Windows the best that it can be. And that's kind of the reason for Surface existing. And it's also to show all the other manufacturers around the world like Dell and HP and Acer and all our Windows partners, what can be done to try and elevate our ecosystem further, so they can look to us for inspiration in their devices, so they can actually make their devices better, which benefits all customers around the world. So that's kind of what we're about. And if you look, this is kind of our current lineup of devices. So we've since 2013 is when we really 2012, 2013 when we really started with the first Surface. We've kind of grown the portfolio a lot in those number of years now. So we'll go from the top and work down. So Duo, and we're on the second version of the Duo. Duo is our foldable device. So you may have seen this in the news, or you might actually have one, or it's been kind of advertised. But this is a foldable device. So this device has 2 screens. It's able to fold 360 degrees. It can act like a tablet, but it can also act like a phone. So it's basically a tablet and a phone combined in one. And it has 2 separate screens. So it's slightly different to some of the other foldables you've seen in around the world. They have 1 screen, but this thing actually has 2 separate panels with a gap between them. And the reason for that is, one, it's a little bit more robust than those bendable OLED screens that we see today, the organic LED screens. They're not quite there in terms of technology. Go here, which is it's just kind of a lower cost device, a little bit smaller.
Mark, can I interrupt just for a moment, please? There has been a request that can you manage to get your slides to up to full screen size by any mechanisms? Apparently,
yeah,
okay.
Yeah, I'm trying. I don't know how to do that, unfortunately. So, whoops, sorry. Previous full screen. See, I'll slide zoom in. I can only see zoom in. Can anybody see that now?
No, it hasn't changed.
Okay,
So,
let me try something else. Hang on. I'm going to stop sharing for a sec.
Yeah.
And let me try this screen. All right. What can you see now? I don't know if you can see anything now. No, that's not doing it. See all slides, toggle subtitles, screen, last view, subtitle settings. Yeah, I don't see. Oh, what's up here? Yeah, I just can't really. There's a zoom button, but it's only zooming on a certain section. What can you see now? Can you see the full screen?
It's a vertical screen bar. Sorry, the things I've just got to get. Can we get social screen? There was a chat. I found I can slide a vertical screen bar to the right to change the balance. There was a comment.
Portion of screen.
Right. Okay. That's it. Wonderful. Whatever you've done is wonderful.
Okay, that worked.
Yes.
Okay, I'll just use this.
Carry on now.
Yeah. Okay. Sorry about that, everybody. But yeah. So going quickly through, because we've lost a little bit of time here. But yeah, the Go devices are kind of the smaller devices that we have in our ecosystem. So a little bit smaller than some of the Pro devices, which is next. So you see Pro 7 there. So that's effectively showing you the 7th iteration of that device. So that's now up to a 13-inch, 13-inch device. It has this iconic kickstand, so it has a built-in kickstand which you can prop it up like a laptop with a keyboard that detaches from the bottom. Now the difference between a Pro 7 and a Pro X, which is next to it, Pro 7 is Intel CPU only in there. Pro X is actually an ARM. It actually runs using a Qualcomm ARM processor, which is custom. So that's got something called the SQ1 processor, which is a co-design between Microsoft and Qualcomm, and that runs a ARM version of Windows operating system. But one of the advantages of using Qualcomm is we can actually utilize Qualcomm's modem. So typically, if you see an ARM device in the Surface devices, it usually means it's enabled with cellular connection rather than just Wi-Fi. So that one has, in that particular one, the Pro X, that has 4G. That's a 4G LTE gigabit connection. Pro 8 is actually just something we just released. So it's kind of a newer version of the Pro 7. Has some extra little things in. So they've optimized the speakers a little bit more. They've introduced things called studio mics, which is basically for more microphones with beamforming. The beamforming microphone will help pick up your voice in a room, and it's better for basically better for Teams calls and things like that. So it's more optimized for kind of this work from home scenario that we're facing with COVID. And then we have Laptop Go, which is a cost down version of our laptop. So it's a still a stylish kind of device, but just less a premium material. So instead of using full metal chassis like we do in most of our devices, it's part of that's plastic just to reduce the cost. Makes it more affordable for educational or just families with limited means sometimes, where they can't really afford the $600, $800 laptop. We try to bring that price point down so it's more accessible for everybody. So it's more inclusive in that regard. And then Laptop 4, fourth, as I said, fourth iteration, comes in two sizes: 13.5-inch display and a 15-inch display. Very beautiful looking device. If you've ever seen one up close, it's pretty nice to look at. And then back in November, we launched this new laptop, a Laptop Studio. Incredible performance on this thing. It has a dedicated GPU in the base, and Intel i7 processors, quad core, 8-core processors, 32 gig of RAM, 2 terabyte of hard drive. Very, very powerful thing. And the unique thing about that device is that screen can actually be moved towards you and then actually laid flat on top of the keyboard. So it actually pivots like an artist easel. So you can actually draw. So it has a pen storage underneath the keyboard, so you can actually pull a magnetically attached pen and draw on that thing. So it's pretty cool actually. And then Studio, which we haven't really updated for a long time, is effectively it's basically a workstation, a compact workstation with a very big screen, 28-inch fully adjustable screen there. And then Surface Hub, which is kind of the meeting room scenario platform. It's just a very large screen with a compute module that's sat in the back, and it has detachable cameras and various accessories there to enable more collaborations. And you can actually put this thing on wheels. There's a little cart that you can attach it to with a very big battery to enable this thing to move from one room to another. So it does some nice things where you can move these around, and you can actually tile them together. They actually connect together. So if you have 2 of them or 3 of them, you can actually tile them to become bigger screens, which is kind of quite nice. So let's go to the next slide. So just quickly, I want to get into 2 devices in particular, and we'll talk about the 2 devices and probably more about the family rather than specific models. But this is the Duo 2, the foldable device that we've been kind of working on for probably about 5 years. I've been working on this for 5 years, even though we're only on the 2nd iteration. It takes a long time to develop these devices. There's lots of unknowns that we don't know about when you're making things like this. So, this is a device that's 2 screens. You can see there the person holding it has 2 screens. It has a very unique hinge in the middle, which enables that 360-degree kind of rotation. And it's a 5.8 pixel sense screen, and then when you open it up into a tablet mode, it becomes this 8.3 kind of inch device. It works with a pen. We have a nice little pen that works with it. All-day battery life, integrated fingerprint reader, and some cameras on the back. And there's a spec list here. Kind of tells you the kind of dimensions. You can go through the display, what the display specs look like. Battery life, you're looking at 15.5 hours of continuous video playback, 28 hours of talk time, 2 batteries. So we have 2 batteries in that thing spread across each half, which is a very unique thing to do, very difficult to actually implement and get right from the battery team. Fast charging. This particular model, the GO2 has a triple camera lens on the back, which is kind of now typical of most of these new smartphones you see these days. You can see all the specs there in terms of resolution and megapixels and video recording ability there. And then into the connectivity part, which is kind of what we're interested in. We have dual band Wi-Fi, MIMO, 802.11ax, so that's 2.415 gig. 5G release, so we're at release 15 at the moment with that. So that's 1.2 gigabits of download speed. Millimeter wave also is enabled on this devices where applicable. So we have band 257, 260, 261. So that's kind of North America. And then we have sub-6. So we have quite a few bands here in terms of not 5G NR and the LTE band. So we're looking at probably like 20 or 30 cellular bands, all with 4x4 MIMO. So and obviously GPS. So it's a pretty loaded device in terms of connectivity. You can take this thing around the world. This thing will pretty much be working wherever you go. You can buy this unlocked as well, which is another thing we tend to do. We don't tend to keep you to a particular carrier. We actually just sell unlocked devices, so you can actually pick the carrier you want. And then going on to Surface Pro X, which is kind of the LTE-enabled laptop, not laptop, but we call this the 2-in-1 product. So it can act as a laptop in this mode, and then detach the keyboard. You can actually, it works as a tablet. This is based on the Qualcomm chipset with a custom silicon from us and them. This is LTE, so not 5G yet. We are working on the 5G version. I can't really say too much about the new one, but it's coming very, very soon. And there'll be some changes to the industrial design of that to make it look better and enable the 5G portions of it. But the LTE version, for most people is still pretty useful in terms of connectivity. I mean, 5G is not everywhere yet, even in the US. It's still not kind of around the whole of the US. So I still have portions of where I live and where I work that 5G doesn't exist. So LTE is still very, very useful. Now, again, this pretty big screen. You can see the dimensions here, some of the RAM options, processor choices, the SQ1 and SQ2. So the SQ2 is just a faster version of the SQ1. Currently we're running on Windows Pro 10 or 11. You can get the upgrade to get 11. Pretty light in terms of weight, 774 grams. One of the things that is very important to us is the recyclability of this product. So, we try to recycle as much as we can of these devices, particularly the metals involved. We try to lower our carbon footprint as much as we can, and that's a conscious decision by Microsoft as a company to become carbon neutral in the next 10 years across the company. So not just Surface devices, but things like Azure, which runs supercomputers effectively. We're trying to make sure that we don't use and actually give back energy to the planet rather than taking. And then on the wireless front here, we have Wi-Fi 802.11 AC, so 2.5, 5 gigahertz bands there, and then LTE, and you can see all the LTE support there. So 1, 2, 3, 4, 5, 7, 8, 12, 13, 14, 19, 20, 25, 26, 28, 30, 38, 39, 40, and 41, 46, and 66. So pretty extensive LTE coverage there. So that's pretty much every band you could think of in terms of cellular enablement across the world. So now we talked about devices. So what do I do and my team do? Well, we design the antennas for these devices, and I just want to go briefly into how we do that. So I only have a team of 10 engineers. I don't have a very big team, actually. Most other companies around the world will have probably 50 to 60 people doing this. I only have 10. And the reason we're kind of down at the 10 mark is because of the way we actually design these antennas. I kind of pioneered the virtual kind of antenna design concept in Microsoft. So nobody was doing this before I turned up. It was all very much building prototypes, being in the lab 24 hours a day and just cutting bits of copper and soldering and making antennas kind of in a very, what's the word for it, simplistic way. And just, it's basically cut, tape, optimize, measure, re-optimize, and that works. That used to be the kind of the way of doing it for many years, but it's not very efficient when you've got other teams involved, like industrial design teams, mechanical teams that are changing things on a daily basis. You just can't keep up with that mode of work. So the only way around that is to basically develop simulation models that are very accurate, and that enables you to change things very quickly in CAD, and then you can re-simulate these things very quickly. And we do that with, in the past, I've had an on-premise, what we call an on-premises supercomputer, and actually that picture you see now is the on-prem cluster that I used to have, and I still do have it. I just don't use it as much as I used to because it's kind of old now. But now we're using a 3,000 core Azure cluster. So we have three different clusters kind of connected together, and they're kind of spread out between the east and the west coast of the United States. Very powerful Intel CPUs in there. Up to 50 terabytes of RAM is available to us. We can use that any way we want. We can split that up into individual simulations. Right? So I can run like 20 simulations. Maybe they only use a terabyte each, or I can run one job using the whole of 50 terabytes. That's very rare, but you know, those things can happen. And then, you know, we're using FEM simulation. So everybody will probably know ANSYS HFSS. ANSYS HFSS is probably the go-to tool for us in terms of simulation capability. I've used other tools like CST in the past. They don't really cut the mustard in terms of accuracy and speed in what we're doing. And particularly for 5G, some of the unique problems in 5G are not really very well suited for CST, is my finding. ANSYS HFSS is really the only tool that we can use for speed and accuracy. And then we have a custom antenna optimization tool that runs on the high performance cluster. I can't really go too much into that, but it's effectively looking at the antenna impedances of what comes out of this tool, the HFSS tool. It goes into another tool, and that runs on the cluster and optimizes the antenna impedances across the bandwidth we require, and has certain objectives and impedance goals and efficiency goals that we must meet. So that's what that tool does. But again, that's custom. And this is kind of the methodology that we're using. We have a concept and design that comes from an ID team, an industrial design team. They all come up with something stupidly crazy like, let's make this device 2 millimeters thick. The screen is going all the way to the edges, so there's no room for any cameras, no battery can fit in here, no antennas can fit in here, nothing can fit in here. And that's where typically they'll come up with what they call a sky blue concept. And then there's people like me have to inject some reality into that and say, well, we can't have zero space for an antenna that doesn't exist. So please give us some space. And all the subsystems will kind of do that argument, and then we'll come to a concept and design that they like, and we'll start. So from the antenna team, we'll start simulating that, and we'll create a very detailed model of the device with the antenna in it, with the screen in it, with the batteries, with the PCB. All those details are in the model, and we'll simulate that and look at the performance. So this design analysis is looking at the performance of those antennas, be it cellular or Wi-Fi. And we'll have specs. Generally, the cellular specs are dictated by the carrier, so AT&T in the US, Orange or EE, BT if they're still going. Hopefully they are. In the UK, they'll have certain they know their network. They will ask for a certain what we call TRP or TIS. So TRP is total radiated power. It's a combination of the antenna and effectively the modem power. They'll have numbers for that. They'll also have the TIS, which is the total isotropic sensitivity, which is the reverse. It's how good your receiver is receiving. They'll have specs for that, and our antennas must meet that in collaboration with the RF team who designs the modem. So we'll go through the design analysis to see if we can meet the specs. If not, we'll go and parameterize the design, and then we'll optimize the design. We'll also look at tolerance analysis, because we are building a real device. We must simulate what happens when we build, say, 1 million of these. How does the antenna vary depending on the batch of the build? You know, each component has a tolerance. It has a mechanical tolerance, has electrical tolerances. All that goes into the simulation, and we go back to the start, and we run this development probably for 4 to 5 to 6 months before we even kick the program off. So, you know, we're doing a lot of work virtually in the world, and the reason for that is because of the changes that come here from ME, E, and ID. They make a lot of changes, and it generally affects the antenna quite a bit, especially the mechanical and the industrial design. The way the device looks and the way it's built really affects how the antenna performs. We're pretty tightly coupled with those two disciplines. And you know, when we first start this concept design, it's usually the industrial design team and the antenna team that get together, because what we do, the antenna really affects the look of the device. It's kind of very tightly coupled there in terms of what the device looks like and how it performs antenna-wise is very important, especially with the industrial design there. So yeah, we're very tightly coupled, and once we're kind of through this 5-6 months of iteration, effectively in the virtual world, we'll come to a point where we're probably not 100% confident in our design. We've probably got a very high confidence in our design, probably 80 to 90% confidence, and say, hey, I think we're at a point now where we can build a prototype. So then we go off and kick off the prototypes, and that is the full device. That is not just the antenna part. That's actually everything, the whole device. And then we'll build prototypes, and then we'll make them. And then what happens is that comes back to us, and we'll start going into the lab now and actually working on the physical antenna prototypes. So that's kind of how that works. And then for those who kind of wondered about what happens when simulation and measurement sometimes don't really add up, and generally they don't exactly, but with our capability that I've developed over the last couple of years, over the last 8 or 9 years now, we're at the stage where we're within, I'd say, within a dB of the real world. So if I simulate something now, and you can see that picture on the left there, that's an actual antenna from an older device, and you can see all the parts that are in there. So you can see the shield cans in there, you can see some of the passives on the PCB, you can see the springs, you can see the chassis in green. That's all simulated, and then we'll look at that. And over time, we've got better and better and better at developing these models. And actually now we're becoming within a dB, I'd say. Sometimes a little bit better than that, depending on the frequency, but yeah, within a dB of the real world, which is actually pretty incredible, to be honest, for something like this. And this is not just for one antenna. We'll have maybe 4 or 5 antennas in the device, and we'll have all those antennas all simulated, and they will be pretty close to each other in terms of what the predicted and the simulated performance looks like. So, and that's really sped up our design cycle, I would say. And then some of the other things that we kind of do internally, which not every company is doing, but we kind of started doing this maybe 4 or 5 years ago, is taking that virtual antenna and putting it into a virtual environment and looking at what happens in that virtual environment. And typically we don't do this for cellular, because it's a much bigger problem to kind of model. We tend to do this for Wi-Fi only devices. So we're making trade-offs in terms of antenna performance specs, because Wi-Fi, there is no real spec in terms of what the Wi-Fi performance is. We have our own internal spec, but there's no carrier, there's no AT&T of the world that's going to tell me, hey, you must meet this spec, because it's kind of, Wi-Fi is it's a very different thing. What the Wi-Fi performance of my house looks like is very different to somebody else's house, because houses are different. The routers are different. We have different types of furniture. We have different types of walls. Just everything is very different. There's no real one model can fit everything. So we try to basically, simulate some various scenarios. This one here is a kitchen. Actually, it's a kitchen in one of our buildings that we kind of modeled, where we found sometimes there's some dead spots. So we kind of modeled it in our simulation tool to find out, hey, what does it actually correlate? And we have data to suggest that there is some blind spots in the kitchen because of some materials. You can see there's a gray cabinet there that's metal, so that is effectively shadowing the antenna from a different router, from a different position, and you can get some weaker spots in terms of signal level, which you'll see a throughput drop effectively in the simulation. And that's kind of what we're doing. So we're kind of looking at throughputs for Wi-Fi and just seeing how that affects design in terms of making a trade-off in the device. Can we actually predict what happens to the throughput, if it's acceptable or not? So one of the things that, since kind of 2017 onwards, there's been a trend in the kind of tablet world, and everybody's seen it, where devices are getting kind of more compact, the screens are getting bigger, but the device doesn't really grow. The real estate of the antenna is getting smaller and smaller and smaller, and you'll see that in the next. You'll see that in the next slide. And here's a trend from 2017 onwards. You can see, antenna area is kind of big with Nokia, Amazon, and then Apple made a big shift down compared to those guys. And then I kind of came on board, and then I dropped that a little bit further. I dropped it again for Service 3, and then Future is even smaller. So we have Future devices again, smaller and smaller and smaller. But the area around the display is kind of where the antennas are sitting, and this next slide will kind of illustrate that for you. And the different approaches the two different companies have taken. So Apple, you can see there's an Apple device there. It looks like a very typical Apple device. It's probably an older one, mind you. They've changed their devices since then, but this kind of illustrates what they have been doing. So they're using this area here and this area here for integrating the antennas. You can see there's roughly a 22 millimeter kind of width here for the antenna, and they've got an LTE receive and GPS antenna here. They have a LTE transmit receive, and prox is a sensor for detecting a human body next to the antenna. So there's reasons for that, and I'll go into those reasons later on. And then they put Wi-Fi on the other side of the device because they wanted probably to reduce the coupling between these two, these antennas here. So Wi-Fi can affect the cellular. We have pretty bands in LTE that are very, very close to the Wi-Fi frequencies. So we need to maintain isolation between those two. And that's what they've done. They've actually put it on a different surface or different edge of the device. Now, our approach was slightly different. We put everything on one edge, which is much more difficult in a smaller volume than what these guys did. But the reason we couldn't do what they did is because this device does not have any real ports. It doesn't have USB, doesn't have a kickstand with hinges. It's very different. It's a very different device. We had to put all antennas at the top because of USB ports, display ports, some charging here, and kickstand hinges. So this kickstand here has quite a big mechanical hinge, which really takes up a lot of real estate. So we were kind of forced to put everything up here. Yes, so you're wondering how we can do it and they can't do it. Well, we had some unique IP that we developed to kind of control the coupling between these antennas on the single edge. The single edge is a very difficult thing to do because all the currents that are induced by these antennas are flowing across this edge here. So they're all kind of intermixed and coupling very heavily if you don't have these mitigations, and we have some patented mitigations. So ISO is one of those things. There's an isolation element in here which kind of redirects the current in a different direction, which helps. Actually, for this one, it'll help this one and this one, Wi-Fi and Wi-Fi. So Bluetooth and Wi-Fi don't really coexist too well unless you've got something like 30 dBs of isolation, believe it or not. A lot of the Wi-Fi chips these days kind of say they can deal with 15, but Not really. It's you need roughly about 30 dB. So we've got some technology in there to help with that 30 dB isolation requirement. Basically without that, we're down in the 12 dB kind of region. So yeah, we've got some nice inventions there that help with that. And then so thinking about the bezel size, as the antennas get smaller and smaller and smaller, the bandwidth's going to kind of shrink. But there's another problem that maybe you are not realizing, that the actual size of the device influences the antenna bandwidth. So here's a simple simulation of what we call bandwidth potential. So it's the amount of bandwidth that you could achieve depending on the length of the device, as in the ground plane length, and the width of the device. So here you can see some curves here that are showing you bandwidth potential depending on the length and the width. So a typical handset these days is in the 130 to 140, 150 range, and then the width is like 60 to 70 millimeters. You can see here, this is kind of where we're landing on a handset, and the bandwidth is actually pretty good. Now on a tablet, which is a lot bigger, so a tablet's a lot bigger in physical size, and everybody might think, well, surely if you've got more room, then the antenna can be better. Actually, it's kind of intuitive. That's really not the case, unfortunately. Tablets are a lot longer and a lot wider than a phone, and what happens is the bandwidth is actually a lot less, particularly in the 600 to 960 band. So these are very troublesome low. These are some of the main frequencies that the carriers like to use because of effectively propagation losses. 600 to 960 has a lot less propagation loss than say 1700 to 2700, which is where the other bands are. So they like to use these bands primarily because of that. For just range and lowering their network infrastructure and penetration into buildings. But for tablets, it's actually a pain because the bandwidth potential is a lot less. It's actually less than half of what a phone is. So designing cellular antennas for bigger devices seems like it might be an easier thing, but actually it's not. It's actually a little bit harder. And that was something I learned very quickly when I first joined Microsoft. I had a background of doing handset design, and to come to tablets, I was thinking, oh, this is going to be a piece of cake. And I was mistakenly, I had to do all this work to find out why was it so much harder to design this for tablets, and that's one of the reasons for sure. And then, if you think that's a problem, we have another problem, which is, everybody likes to put ports, speakers, microphones, IR sensors, cameras, speakers in these areas. So these areas up in here and here are kind of the key areas for the phone, the antenna implementation. But guess what? People want to put other things there as well. So that even makes the room even less available for us. So we have a lot more reduced space than we would normally have, unfortunately. And then let me add on again. This was the world of the 3G, 4G era where we only had 4 antennas to worry about. So we're now moving to 5G, or we are in the process of moving to 5G. We have more frequency bands, we have lower frequencies. So we're now looking, in the US, we're looking at 600, well, we are doing 600 meg antennas, which is very difficult to achieve on something like a smartphone or a tablet. And carrier aggregation, where you're actually adding bandwidth from different portions of the frequency spectrum to add, basically improve your throughput, and also MIMO. So now you've gone from 4 to maybe 6 to 8. Now I've seen actually 10. I've seen 10 antenna implementations done, not particularly with us, but other companies. They're doing that, and that means that real estate is getting very, very, very tight. And how do you do all that? I mean, that's very difficult. And then obviously the trend in the industry is to do what we're seeing here on the left is, we have these very thick, what we call bezels on the edges. And as time has gone, we've kind of shrunk that bezel down to give everybody a more real estate in the product. But, the bezel's got very, very small, but unfortunately that's where the antenna needs to sit. So you've now kind of shrunk my antenna volume by quite a lot, a significant amount. And, you can run a simulation here. And this is kind of just a very simple low band antenna, kind of centered around 900 megahertz. So we just one frequency measured, simulated what that would do, and we just basically shrunk the antenna volume from 12 millimeters in width So the length is constant. So whatever the width of this device would have been, 70 millimeters, say, kept that constant, but we shrunk the width from 12 down to 5. And you can see, you know, it changes frequency a little bit, but not much. But the main thing is the radiation efficiency of the antenna over the frequency. You can see it drops significantly. You know, we went from nearly 90% here down to kind of 35% here. But you know, over the bandwidth, it's pretty poor. So we're actually trying to cover this 600 to 960 band here, here, and here. In the old days of 12 millimeters, you could have done that with one antenna, could have done everything, and probably just a very small passive match would have covered that bandwidth pretty nicely. But now you really can't. It's looking pretty dire here to do that. So that's a problem for sure. And then this is kind of just explaining, you know, what happens when you have this trade-off, this what we call the trade-off triangle. You have the size of the antenna, you have the bandwidth of the antenna, and the efficiency of the antenna. And you know, as things get shrunk down, you're trading one thing for the other. So we're trading size for either efficiency or bandwidth. So you can have a very narrow bandwidth but kind of good efficiency, or you can have a wider bandwidth with poor efficiency. And this is kind of what this is saying. It's saying, you know, what happens when you trade these things off. As you can see, ABC, you can see what happens when you're reducing here. That the bandwidth is shrinking, but you know, the efficiency of the antenna is actually pretty good at a certain point, but across the band, it's definitely shrinking. So you know, and when you're trying to cover these wide bandwidths, that's a real problem. So you know, how do you do that? How do you overcome this problem? And this is kind of what we're going into next. Is well, there is a way of doing it, and it's been around for the last couple of 5 years. 5 years definitely has been around, maybe 8 years, but really in the last 5 years it's come to its own, and it's called basically we're electrically now tuning antennas. So we don't really use passive. We use passive components, but we now are actually swapping these components out to actually tune the antenna to different frequencies. So here I've got some very simple diagrams of an antenna and kind of how you would do it. So here you can see an antenna here with the RF front end, with effectively the modem is into the feed of the antenna. There's a ground connection here, and what we've done is we've added what we call an aperture tuning element. So we've added a component here that will change the current distribution of the antenna, and we're able to swap these in and out via a switch. So we have some RF switches that will swap different passive components out, and we can actually electrically tune the antenna to a different spot in the frequency band. The other way of doing it is actually one of the problems with the antenna getting smaller is that the impedance bandwidth can't be matched to 50 ohms across all frequencies. So another method is actually kind of using similar concept but for impedance matching. So we can actually try and impedance match the antenna across the frequency band of interest with kind of like a tunable capacitor is one kind of element that we kind of use with switches in combination to effectively have a pi match that is reconfigurable. So we can have say a 3-element pi match that we can maybe reconfigure it with different values to tune over different frequencies. That's one way of doing it. And then there's also this hybrid method, which is actually both. And this is kind of commonplace now with some of the higher smart end phones and tablets. The antenna volume is so small that we can't really just rely on one or two of these kind of techniques. You have to employ both techniques at the same time to try and tune the frequency and then look at impedance matching that new tuning frequency band. So yeah, it gets very complicated. So imagine having 6 to 8 antennas that are doing this. It's very, very complicated to kind of do that. And this is kind of a pictogram of what we're doing. You know, when this switch, this is an SP4 switch. So this is a very simple diagram of this is what we call a PFIR, planar inverted F antenna, feed ground, and then we have a switch that has some different passives connected to ground. The natural resonance would mean this switch is open. So this natural resonance here this is what the antenna would naturally do without any switch components. And then what we can do is we can swap in some capacitors in here. That will lower the frequency, and as you can see, you can tune the frequency down. There is a small shift in the efficiency because these switches aren't lossless. The components aren't lossless like we're using. They all have a certain Q value. This has a certain resistance to it. So you do try. There is some degradation of the efficiency, but it's a lot better than the natural decay of the antenna across that band. You can see the efficiency is much better here much better here than it is here, because we've actually tuned this thing down, and we can actually do it all the way up to the top as well. So you can tune it up depending on the antenna structure and what components we're using. So that is improving this what we call the TRP TIS, which is basically the carrier specific metrics that the carriers want. They want us to hit these real high efficiency numbers, and you may see -6 here. That's 25%. That's a 25% number. That's actually a very high number, believe it or not, for low band. I know it doesn't sound like it to an antenna engineer, but 25% is actually a very high number for 600 megahertz. The days of 40-50% antennas don't really exist anymore. The antennas aren't capable of getting us to that spot with the volumes that we have today. So that kind of addresses the low band problem as the size of the antenna was shrinking. But eventually what happened is the volumes got so small now, we're actually having problems in the higher frequency bands. So 800 meg, 1800 megs, more than 2 gigahertz, we're seeing the same problem where we can't really match those frequencies either. So we've had to incorporate not just one tuners. We actually now have possibly up to 3 different tuners in a device per antenna. So it's getting very, very complicated. You can see here there's a very simplified pictogram of an antenna, and the voltages are present on that antenna depending on the natural resonant frequencies of that antenna. So 900 megs, you can see that's what we call here. That's the first resonance. Then we have the second harmonic, the third harmonic, and the fourth harmonic. And what we try to do is we use these resonances and to actually put, and you can see here, to put the tuners at specific points at the highest voltage levels for these harmonics, because that's where the tuner has its most influence. So you can see here we have a tuner just to the right of the feed. So that's the feed here, and we've picked that spot because if we pick it up here, we're probably playing around with the mid band and the high band frequencies at the same time. So what we want to do, we want to have independent control of the low band without disturbing this one or this one. So that's why that's specifically placed here. And the only way you can do this is through simulation. Again, we look at simulation. We kind of integrate. One way of doing this is to integrate the field from here to here, and that will tell you the voltage across that antenna. And we plot those integrations across the antenna, and we pick, with optimization, where the best spot for the tuner is. And so you can see here we're independently tuning the low band. This one here, with this position here, is tuning 1700 to 2.2 gigahertz, which is another kind of area of interest for the cellular connection guys, the AT&Ts and T-Mobiles of the world. And then the high band, which is another frequency band they like to use, us 2.5 to 2.7 is kind of the band there, which is what we call the high band. So that point there will independently tune. There is some effect here and here, but it's a lot less. So that's how we're kind of combating this problem with antennas and tuners and making the antenna very small. So I think with kind of some of the background on what we're doing, I want to go into a video here of one of the devices we launched, and hopefully this video will work and not die on me. So let's see if I can play it. And for some reason, it's not playing now. Which is interesting. Why is that? Oh, here we go. Okay. Hopefully you can see this. Whoops, what there?
Oh, sometimes I get a feeling, yeah. I get a feeling that I never had before. No, no. Hello? I just want to tell you right now that I believe, I really do believe that something's got a hold on me, yeah. Oh, something's got a hold on me right now, yeah. Let me tell you now, I've got a feeling I feel so strange. Everything about me seems to have changed. Step by step, I got a brand new walk. I even sound sweeter when I talk. I said, oh, 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 hey, baby, oh, it must be love, it must be love.
So that was the Surface Duo. So that was a little video, and this is kind of the devices and the device and how it's used. So we have all these different use cases. We've got tablet mode, kind of phone mode there. You can see with a pen, you can see we can do some little sketches. There's like a more laptop kind of mode there with the keyboard. Looking at photos, you can see the collection of photos you got with one particular photo on the other side. What we call temp mode, you can watch videos in that mode, and then there's what we call peak. So this device is very highly configurable. It has very different modes, and that causes problems for also the antennas again, because what we're doing is we're varying the ground plane. So remember I said the ground plane is the length and the width, what that looks like in terms of length. Well, yeah, that's very difficult when you've got something that actually now varies. So a phone or a tablet generally has a constant ground plane, but this device actually has a variable ground plane. You can actually change the way the ground plane interacts with the antenna, because maybe you want to angle it in a different way, and that electrically changes the antenna. So it's kind of difficult to kind of design for that, and that's why those tuning techniques are kind of very, very useful for us. So yeah, and just going through, I want to go through quick because I think we're kind of short on time, I think a little bit, but you know, you can see here all the cameras, all the earpiece and the proximity sensors, and you know, this is the area where the antenna is. So you can see it's already chock-a-block with microphones and cameras. It's 11 megapixel camera and a big earpiece here. So we've got to try and fit the antenna in here without degrading the antenna too much. There's some antennas on the side here. So you know, we have Wi-Fi in this corner, and down here you can see there's volume buttons. There's a fingerprint reader here. There's the SIM tray itself here. So we've got to try and integrate the antenna somehow in this area. And also the USB-C. So the main antenna is actually taking this portion of the device up. So we had to accommodate this big USB-C connector, which is obviously metal. So that's something else we had to kind of try and do. And then here's a kind of X-ray X-ray shot. You can see what's inside. It's not really an X-ray. It's more of just a see-through shot. But you know, antennas down here. There's an antenna here, antenna up here. They're not across the top. And that's kind of the state of play and the real estate on this device. And here's some dimensions. So you know, in this mode, when the screens are back to back, you can see it's only 145 by 94, but in terms of ground plane length. But now when I open it up, it's 186 by 228. And if I went back to that slide earlier on showing the difference in the bandwidth, you know, this is a problem. This bandwidth is a problem because the bandwidth available to me is a lot less than it is in this configuration. So I get good performance here, but I get bad performance here. And you can actually see how thin this device is. It's less than 5 millimeters thick on each side. So that's very, very thin. That's the thinnest, probably the thinnest, I think it still is the thinnest kind of device in the world in terms of cellular phone calls. And here's some of the shots inside the kind of the the device. So this is the main the antenna, and this is actually a patented design. Unfortunately, they've looked like they've peeled off some of the antenna here. So you can see this is a plastic shell or a plastic frame, mid frame, and then there's this gold pattern that's kind of printed on the plastic. Now, that is called LDS, and that stands for laser direct structuring. It's a really cool process. I'll show you, there's a quick video of that later on. It's a nice process where this plastic has a special chemical in it that's activated by a laser beam. So what happens is we put this blank plastic into the machine. We actually laser this pattern on the plastic, and what it does, it activates this chemical inside the plastic. And then what we do is we dip this plastic into a bath of copper ions, and the copper ions actually adhere to the activated parts of the plastic, and that's how you get this antenna pattern. So this antenna is it's a double coupled loop antenna. It has a feed mechanism here, a little kind of short monopole looking thing, and there's two gaps either side, which is effectively capacitive coupling. So I'm coupling some energy here, and this is grounded at this end, and that has a tuner at this end. And then so that's, you can see by the length here, that's probably the longer 700 to 960 band is this side. And then you can see here there's the ground point here with another tuner and a short element, and you can probably deduce from that it's the higher frequency of the cellular band. So this antenna here, low band, this antenna here, high band, and the gap, you can see the gap here and here is slightly different because I'm actually introducing different types of coupling between this element and this element to kind of control the impedance of the antenna. And there's a feed here and a ground connection here. Let's move on. And then this antenna, which is kind of at the top of the device on the corner, this does a few things. It does MIMO, so it does the 1700 megahertz to the 2.7 gig. It also does Wi-Fi. So this actually incorporates a concept called antenna sharing. So we actually multiplex different protocols into the same antenna. So we're able, in some cases, to share antennas that do very different jobs. One's doing the receive MIMO part of LT. The other radio is actually connected to this, is doing Wi-Fi as well at the same time. And that's one way of reducing the number of antennas in the device is using a antenna sharing concept. Again, this is kind of another coupled, if you look at it, it's another coupled element. So we have a small driven monopole here, which is doing probably resonating at 5 gigahertz or roughly there. And then you have this grounded section. So you can think of this as a distributed L circuit. If you think about it, this is an inductor effectively with a little gap between it and this driven element, which is a C. So you got an LC circuit here, and you can and what's an LC circuit do? Well, it can resonate at certain frequencies, obviously. So you can design this element in congregation with this element to actually resonate across a wide bandwidth, and that's what we've done. We've got this to work at pretty wide frequencies because of that type of antenna design. And here's the antenna down the side. So this is very simple looking antenna. We have a feed and two grounds. So this works again. This works in two different modes. It has a monopole kind of PIFA mode with feed and ground here, and then it has a ground here, which if you look at that, it looks like a loop antenna. So it has two modes of operation, and that's another way of getting extra bandwidth out is introducing two modes of operation. One monopole PIFA mode, one kind of loop mode, and one works at one frequency, the other works at a different frequency. And we usually put passives in these ground sections to kind of either short circuit or open circuit at different frequencies, so we can control where that antenna actually operates. So this does Wi-Fi and MIMO again, and it's very compact. It has very little space here. There is very little real estate for the antenna to live on because the display is really up to the edge here, and that was one of the challenges of putting the antenna here. Is because of that, but there was no other place to put it, so that's kind of the trade-off we had to make at that point. And then, going further up to the top again, we've got kind of a combined antenna here. There's a feed in the ground here. Actually, there's a ground here also, actually. And actually, it's not. It's actually feed ground, and then there's a feed ground here. Sorry. This is a GPS. This is actually the GPS antenna for this device. And then on the okay, it looks like we didn't have. There was supposed to be another slide, but here and here, if you can see here, there's a feed in the ground here, and actually you can just see the antenna actually coming down here. It's actually below the GPS antenna. That's a low band antenna, receive only, and what this has a impedance tuner on it, so we couldn't get the full bandwidth of this antenna out because it's just in such a small volume with the cameras in this area. You can see the camera cut out here in the frame, so we had to use an impedance tuner to kind of match that antenna across multiple frequencies. And then I was going to go through this LDS. There's a video on LDS, but I think we'll have to skip it because of time and things. But LDS is this process, with this gold plating on the plastic, and this is the process for it. So it's an injection molded part, and then we use a laser to activate the plastic. So there's a special chemical in there that gets activated, and then also the laser actually forms a very rough surface, or micro surface, I should say, on the plastic. So the copper can actually get adhered to that rough area. And again, we're putting this into a bath of copper, basically a copper bath, and the copper kind of adheres to that area where the laser has been and activate the chemical, and that gives you the plating. And this is kind of used in it's been used in the automotive industry for many years, and it was very popular in the motor industry. But it's kind of definitely been kind of taken on by the antenna companies and people like Apple and us and Samsung, and all those tier 1 players have been using this for probably many years now. And one of the other things that we have to worry about in terms of antenna performance is SAR. So SAR is what we call the specific absorption rate of the device. So it's the amount of energy that the device gives off and what's absorbed by my body. And we have quite strict rules in the US compared to Europe. So Europe has a very I won't say lax, it's a very safe limit, but it's very different to the one in the US. The US is very strict. So FCC, Canada, very strict limit of 1.6 watts per kilogram, and that's only averaged over a gram. And depending on the device, there's different test paradigms for tablets versus handsets versus phablets. So tablets have the harshest of all tests. It's what they call a 0 millimeter test. So basically, you have to measure the SAR at 0 millimeters away from the body phantom, which means you're basically getting a full blast of the RF right at the surface of your skin if your skin was on the laptop, or the tablet. So that's the harshest of all testing compared to a phone. A phone has a different test. It's actually on the ear. They don't really do the full body, because the use case for a phone is not on the body. It's actually on using it as a phone call. And there's certain edges that you have to test on. There's kind of tilt. They tilt the phone in certain directions to kind of simulate how you're holding the phone, and they'll measure the SAR doing that. And then phablets are kind of a combo of this and this. And EU has the same, but the limits are very different. So it's 2 watts per kilogram, but over 10 gram. So the averaging over 10 gram is 10 times this. So it's a little bit easier to meet the SAR limits of Europe. And on tablets, you would never meet the 0 millimeter requirement of 1.6. It's just impossible, especially with the transmit powers that we're using. So typical LTE modem is pumping out about 24 dBm into the antenna. At 0 millimeters, your SAR values are probably in the 15 watts per kilogram range. So massively different to this. So we have to employ SAR mitigation to make this legal. And generally what we do is we have effectively a proximity sensor inside the device. So we have a proximity sensor near the antenna, to actually stop it from transmitting so much. Well, what that does, it just actually is a capacitive sensor, so it actually detects your body near the antenna, and once it does, it backs off the power until your body is nowhere near the antenna. So that's kind of how we're doing it. And then there's some quick pictures on how you measure SAR. So we have a DAISY, what we call a DAISY 6 here. And this is a robot that we have in a lab. This is not our particular robot, but it's super similar to this. And this has a E-field probe that goes into a liquid that simulates your body, the body properties. So the dielectric constant and the loss tangent of your body. It's kind of simulated by this liquid. And the device, as you can see, is kind of sat underneath this kind of phantom here. So on a phone, you can see here, you can see the phone headset is actually by the ear here, and then this probe is going down inside here, and it's measuring inside here what the SAR is like at that particular point. And we do that in a certain area, and we make sure the SAR is not above a certain level. And then on this particular one, you can see, it's hard to see, but there's a tablet in here. And that, yeah, the antenna is somewhere clearly here, and we're measuring the same thing. We're measuring the SAR at this point here, but here the antenna is actually at the point where we want to measure. On a phone, generally we're transmitting at the bottom. We're transmitting down here for the phone, but the actual SAR measurement is actually by the ear. So there's a big distance. There's a big distance here to here. So that's why phones kind of can get away sometimes with having lower SAR values, because really the transmitter is at the bottom of the phone, not the top where the SAR is actually measured. And then, as I was saying, proximity sensors are the only way you can really get away these days with having a 0 millimeter SAR test. So in our devices, we have a capacitive sensor near the antenna, which detects when a body is next to the transmitting antenna. So we're allowed to have space between the device and the phantom, depending on how good the design of the sensor is, and also how much the antenna radiates. We're allowed a certain distance between the phantom and the tablet itself, and we can pass SAR that way, as long as the sensor is detecting a human body next to it. And that's kind of one of the mitigations of getting around the SAR rules there. And then on our tablet device, because, well, our foldable device, I should say, our device is kind of a unique thing where it does all these different postures. So you can see all these different postures here. So it looks like a phone in some cases, and then in some other cases, it looks like a tablet. So for us, this is why we took a long time developing these devices, is we have to combat all the SAR cases for both. So depending on the angle, and we have sensors in here actually to detect what the angle looks like between this device from this face and this face. We can tell what mode we're in, and we will apply a different type of SAR mitigation depending on the angle of the two screens. So that's kind of one way of us knowing how to pass these tests, is because we can actually work out which angle or what mode we're in, and then we have software algorithms that are working out constantly what the SAR mitigation can be. And one of the things that we did was, the antenna that you saw in the previous slides, the double couple loop, it actually has a sensing mechanism built into the antenna itself. So this is one of my patents back in 2018. So you can see how long I've been working on this foldable design. 2018 is always, I can actually file 2017. So January of 2017. So you could probably go back another year. We were working on this concept back in 2016. So that's 5 years ago. So we've been doing this for a while now, where the antenna works as an antenna, but it also has a method of using the elements as a capacitive sensor at the same time. And that's one way of integrating the antenna functionality with the prox sensing functionality to detect if something's next to the transmitting antenna. And then we have another patent on using sensors and algorithms to work out what is the difference, the angle difference between these two devices. And in conjunction with this idea, we can actually detect what mode we're in, if there's a human next to us or not, and then we can apply a different type of power reduction in the modem to do that. Mike, how are we doing for time? Because I want to be conscious about time, but we've still got about 10 slides to go. Do you think we got time still?
Well, yes, I think you should start wrapping up. So why don't you sort of just say a couple of words for each side, say what they are, and then, because we are collecting some questions, and
okay, awesome.
We would like to have those answers. So go ahead on that, okay?
Yeah, I'll skip the video because I think it's a couple of minutes, but I'll skip the video. And we're going straight to the Surface Pro X device. So again, I'm kind of showing here button location on the side here, another couple of ports and button location on the other side. And then where the antennas are, we've got cameras, microphones, dual microphones, not just one, we've got multiple. LED notification, and then you can see here there's ambient light sensors. Proximity sensor in this case is not for antenna reasons. That's actually working out if I need to switch my device on because there's a human approaching the device and I need to wake up, effectively get the device from sleep mode to actually activate. And then you have IR front camera here. So the IR front camera actually is very noisy. It's a very electrically noisy thing, which is not good for antenna receive sensitivity. But that's our face recognition system to sign you into the device. Then the kickstand here, and then this is kind of the antenna deck, as we call it, that runs across the top, and you can see how jam-packed the antenna deck is. It's basically full of gold. Which is the antenna. You can see here at the top here, there's a single antenna here, LTE transmit receive. It's very hard. I know it's pretty difficult to see, but you can see it wraps across basically two surfaces. Well, actually three surfaces if you count the connection here. But you can see it looks like a loop antenna. Actually, it is a loop antenna. I have fondness for loop antennas because of my PhD and Mike's influence for many years on loop antennas. So this actually loop antenna is a tunable. So this is a tunable loop antenna, and it covers this band 970 to 960. The next antenna highlighted here is a single 1700 2690 antenna. And then if we quickly move on, we can see there's a Wi-Fi antenna here, which is a kind of another couple. I have a fondness for coupled structures because they have very good wideband characteristics to meet the kind of the bandwidth requirements. So this is a monopole, kind of meandered monopole here, and then you can see there's a grounded structure coupled to it, and that combination works very well for coupling energy. And the thing next to it, if you're wondering, is it looks kind of weird and arbitrary. It's actually one of the devices that help with the isolation between this guy and this guy. So this LTE antenna here and here, and this Wi-Fi antenna here kind of operate at nearly close to 2.4. So the filters that we're using in this LTE don't have enough of a steep roll-off to stop all the interference that could happen, or LTE from interfering with Wi-Fi. So we have to try and enhance the isolation between them to improve that. And this structure here was actually developed using an AI algorithm. So we developed an AI algorithm to actually work out what it should look like to improve the isolation. And that's what it came up with, and it actually works pretty well. And then on the other side, quickly, there's a Wi-Fi antenna here, which is the sister to the other one. There's a GPS antenna at the top here, and that's across going through three surfaces. And then you've got the RX only 1700 to 2700, and then the RX only antenna here. And there should have been something here. I don't know why that's missing. It's kind of interesting. And one of the, quickly just going through the mitigation in a tablet, we have actually a very nice way of mitigating the SAR in a tablet, is because when we have the keyboard in the device, we're actually classed as a laptop, and laptops have very different rules to tablets and phones. So on a laptop, the SAR is only measured from the bottom of the keyboard section. So if we have a keyboard injected, we can actually claim that we're a laptop, and they will measure SAR here, but the antenna's up here. So there is no SAR issue when we have that. And actually we have this algorithm that has again, we have a sensor in here and a sensor in here to look at the angle between the keyboard region and the display region. And we can tell, where are we in laptop mode? So we have rules on what is classed as a laptop mode and what's classed as a tablet mode. And because we know the angle, we can instigate what type of mode we're in, and we can say, well, actually, now if I'm between 0 and 45, I'm laptop. If I'm 46 to 210, I'm still a laptop. But if I'm now 211 to 360, say C and D, which is here and here, the FCC classed that as a tablet, and we have to back off the power to become within the regulation. So we have a stipulation that we must go into a tablet mode, which means backed off. But actually what we do, we're a bit cleverer than that. We have a sensor inside here. So the sensor is actually sat right under the transmit antenna suite. And this is what we do is we use the tablet mode to say, hey, we're in tablet mode, but please don't back off the power until this sensor is activated. So we have a second condition saying, yes, we're in tablet mode, but I only need to go back off only when the sensor is activated. And actually the sensor is very unique in itself. So this is more or less done now, but this sensor is not a typical piece of copper. So usually capacitive sensors are usually made of copper. This is actually something we also came up with back in I think it's like 2014. This is an ink jetted, this is actually an ink. We have an ink in here where we have electrodes that are attached to the ink, and the ink is resistive, and we can control the resistivity of the ink to a certain point, and we can make it resistive enough, have enough resistance so it's actually transparent to the RF of the antenna. So the antenna does not see it. It's actually transparent to the antenna because this has a resistivity that's high enough that it's transparent to the antenna, but it's low enough for it to support a static E field. So there's I'll say static, it's a very low kilohertz signal. There's an oscillator on here that's generating a very slow kilohertz signal on the sensor. And what happens is, as you can see in this diagram here, if a hand is coming close to this sensor, then what happens is you're basically measuring the capacitance difference between this plate and my hand using the oscillator, and that basically gives you a change of capacitance. And that's effectively how we know there's an object that's probably a human next to us. So with that, I will end the presentation, and thank you very much.
Right, thank you, Mark. Just putting myself up, and right, we've got quite a lot of questions. I'm going to have to group some of them to be able to answer them. Probably that's the best way. But I am going to ask the first question, which you part answered, which was, do Apple use your antenna? Well, now I know the answer to, since you worked at Microsoft, but my question is, when you were working for Antenova, did you have a relationship with Apple at that time?
Yeah, we did. We before they did iPhone. So they were doing laptops. They were doing laptops for a long time. So I personally didn't do any of the design for the Apple products, but my colleague who was there at the time, we were engaged with Apple in some programs. It's such a long time ago, I can't remember, but it was more of the laptop stuff. And actually, one of the people I used to work with called Rob Schlub. So I used to work with Rob. Rob actually got recruited from Antenova to work at Apple, and he was actually their first antenna designer for handsets at Apple. So there's a history of Antenova and being in like some of these prestigious companies like Microsoft and Apple because I effectively came to Microsoft to kind of do the same thing as Rob did for Apple. But yeah, these antennas are kind of, they've kind of been birthed from the same place in Cambridge in some ways. Yeah.
Right. There's a comment from that was from I think it was Dave Stewart, but anyway, right, Andrew Levy, when we were talking a bit earlier about your problems of different frequencies,
Yep.
I sympathize with you, Mark. When I worked for this, that is Andrew Levy,
Yeah.
worked for Jaguar Land Rover, we had similar problems, but with frequencies from long wave to millimeter waves with limited real estate. And he says you're doing excellent work. No need to comment, but just take the plaudits on that.
Yeah, thank you.
Right. The next question from Dave Wellesby. How does the orientation of the mobile affect the antenna performance? But I think you've probably answered that by in the time after the question was asked. But is it better to hold it rather than lay it on
Actually, holding is a problematic thing as well, because the human body is an absorber. It's a pretty good absorber. So, you know, there's a lot of attenuation when you hold something. So, I mean, the 600, 700 megahertz, if you hold the device, you're probably degrading the antenna by 7 dB, roughly.
Wow, that's
a lot.
Yes.
Yeah.
Okay. There's a lot of similar questions, but which was this is from Mr. S. White. What effect does holding the device have on the antenna? And does holding it to your head vary it to holding it to your lap? Well, you've sort of answered that on that. And do you have to model the human body for different?
Yeah, one of the things we do, absolutely. To kind of predict what the SAR is, because sometimes we have designs that have so high a SAR that you just don't want to implement the design. So yeah, we model a human body for sure.
Then there's another one related question. How would this was from Philip Brown. How would you allow for antenna detuning due to human body finger proximity? So that's a detuning, not efficiency thing.
Yeah. So sometimes it depends on the antenna type. Sometimes when you hold something, it'll just give you a better match because it's just loss. It's just really, you're just improving the 50. You make it look like a 50 ohm device, but there is cases where the antenna does detune. And one of the things about those antenna tuners that we were talking about, there is mechanisms in there to detect the detuning and to compensate. So all you're doing there is you're changing the impedance of the antenna a little bit to try and pull it back into the frequency of interest. So there is active methods to actually compensate for that. But sometimes doing that actually is lossy in itself. So it's difficult. It's a trade-off again.
Okay. Then from Ian Simpson, this slightly politically oriented question, which is, so hands-free usage of phones should be considerably better than to-ear usage. So it's okay. Answered it. That's excellent. There's a question also from Ian Simpson, which is answered to everybody. Will the lecture be available to see again as a recording? The answer is yes. And is CPD sophistication available? And the answer to that is yes. Go to the Sussex IET website and you'll be able to interact with that and get the CPD results on that CPD points. Right, is polar diagram gain versus direction? Yeah, is that an important thing?
Yeah. So for cellular, yes, we want to be omnidirectional as possible for sure, because I don't know where the cell tower is, so I want that antenna to have kind of I try to make it as constant gain around the device itself. So I don't want anything very peaky in terms of antenna gain. For cellular Wi-Fi, because you're in a building, kind of the fact you have reflections, kind of, if you have a very high gain Wi-Fi antenna, it kind of gets averaged out because of the internal reflections inside the building. So it's not as important to have a omnidirectional Wi-Fi antenna as it is for cellular, because generally cellular outside, or you just don't know where the cell tower is. But in Wi-Fi, you can get away with higher peak gain antennas, but the building and the reflections from whatever room you're in kind of average average that peak gain out for you in terms of what happens to the signal. So yeah, they are important, but they're not. We really focus on getting the bandwidth across the antenna and maintaining the efficiency of that antenna across that bandwidth. And also the amount of SAR. Those are the three top kind of metrics we look at. I mean, this is important, but it's not the one we optimize for. We're optimizing for different things. Yeah.
Okay, right. There's an interesting one here. Is there an intuitive explanation of their efficiency goes down as ground plane increases? Would have thought, Martin Thorpe would have thought that would improve things. So do I.
Yeah. So yeah, it's interesting, isn't it? So on a phone, that the size of the phone is actually resonant. If you hit it with a plane wave in simulation, you will get a reflection out of it, and you'll see the energy scatter back at a certain frequency, which is, depending on the size of the phone, roughly at 1 gigahertz, which is kind of close to the 600-700 megahertz. But if you do the same thing for a tablet, that energy, that resonant frequency of that tablet is actually nowhere near 600-700 megahertz. It's actually probably down in the 400-500 megahertz area. So what the problem is, it's that structure, that ground plane is not a resonant structure at the frequency we want. If we wanted to make a TV antenna like 400 megahertz, that would be perfect. That type of ground plane is actually really good for that, because it's naturally and that's why. Yeah.
So it's resonant at the wrong frequency. Okay. Yeah. Now there's why do all the antennas use gold plating rather than cheaper base copper? Does gold behave better as an antenna?
No, it's oxidation. It's oxidation. So you look at the copper, and they usually put they'll put some other, like maybe tin or nickel on top of that, and it oxidizes. So we kind of want to reduce the oxidization over time. So we put put gold on there to reduce the oxidization. It's a very, very thin layer. It's like 2 micron. It's a very, very thin layer of gold. Doesn't cost too much. Fingers crossed.
Yeah. Now that was from Mr. S. White. This is an anonymous attendee. How do you avoid doing an Apple and end up telling users they're holding the device wrong and shorting antennas with their fingers?
Yeah, and I think that is, so there's a story behind the Apple, and it's of what they're having. I don't want to go into it here, but yeah, basically, we've learned from that lesson. So they were the first to do it, and they learned the hard way by not probably testing enough. And we make sure. I mean, we're kind of aware of the problem, so we don't. That's why sometimes it takes more time for us to release something, because we found there is a problem down the road, and we've identified it and corrected it. So it's basically we're very aware of that particular problem, and that was a learning experience for them, and it actually taught the industry a lot. So yeah, we've learned those lessons, and hopefully we don't repeat those lessons in the future. But yeah, good point. Yeah.
Okay. David Walesby asks, we are moving towards spatial diversity antenna. Is this going to be supported, or is it this MIMO or spatial diversity, or what?
It's. I mean, we have that as well. So it's coming. I mean, 5G. I'm guessing he's talking about the placing antennas further away from each other. Is that kind of what I think the question's about? But I mean, that will. So if you look at 5G devices, we can't fit 6 to 8 in the same region as we have been. So they are moving around more the device these days. So yeah, I mean, spatial diversity is definitely something we're conscious about, and we're doing, yeah, for sure. Yeah.
Okay. Talking of 5G, by the way, I have got a 5G phone here, but it is Samsung. But anyway, and I can't get a signal here. You know where I am near.
I do. Yeah, absolutely. Yeah.
But
surprising.
Anyway, yeah. But it's all right when I go to Crawley or to somewhere. Anyway, right. GPS antennas, Mr. S. White again, are GPS antennas directional, and does directional not matter for these? You assume this would...
It's kind of. So we have cellular assisted GPS. So if this was a standalone GPS device, you know, you'd always recommend probably an RHCP type of antenna to match with the satellite, what's coming down from the satellite. But you know, because these devices have cellular enabled, they're assisted. So what happens is the inference data is already given to the device. So the GPS knows roughly where to look straight away in terms of where the satellites are. So the time to lock is so much quicker than maybe a standalone device would be. And you know, we can't really fit a RHCP patch antenna into a device like that thin, that small. And if you start shrinking the patch antennas to that size, you basically end up with linear polarization anyway. So, and that's what we're doing. We're just basically making, if we can, the highest efficiency I wouldn't say omnidirectional, but we try to consciously get the antenna to look up into the sky if we can. So that, you know, there's some optimization there for that particular antenna to try and get it'd be useless pointing to the ground. So we try to optimize it so it's looking up to the sky if we can. But yeah, usually it's just a very as high a performance as we can linear polarized antenna, and usually we try to get as much RHCP out of it as possible. So you know, that's kind of the technique we're doing, because we don't really have the luxury of the room to do anything else. So that's the thing we do. Yeah.
What I'm going to do now is to read out some questions, and you can pick out which ones you answer and which you don't, because we really are running out of time.
Yeah, sure.
Before doing that, thank you. There's a thank you from Paul in Germany, and earlier on there was a thank you from somebody in France. So you can see it is getting around the world, and at least in Europe. So right, the questions are. First of all, from Anonymous, do you need to measure a phone in the shirt pocket for the SAR figures for EM safety of phones with planted medical devices? So,
yeah, so it wouldn't be a shirt. So we wouldn't do a shirt pocket. That's called a body. So that's the body. So the body SAR test I was referring to, which is the 0 millimeter test. That would be the equivalent of a shirt pocket. So yeah, so the SAR there has to pass that very strict limit of 1.6. So yeah, we don't constantly do it for implanted medical devices, but it's attached to the regulations for the 0 millimeter body test, I think, for that reason. So yeah, we and the US one is the strictest one. So if you pass the US one, you can pass anything, and that's the only one we care about, because that is the hardest one to pass.
Right, another quick question, probably yes/no answer from Marek. Are the magneto-electric antennas being considered for phones?
Not if I know of.
Right. Next one, are pin diodes still used for active tuning?
No, not at all. I don't think they've ever been used commercially in cell phones, as far as I know. Maybe I'm wrong, but I don't think they've ever been used. Yeah.
Okay, Steve Barlow then asks, do SAR mitigation sensors have to be treated as safety critical?
Absolutely. So we have backup. So if the SAR sensor fails, there is software in there that backs off the power 100% all the time. So let's say my SAR sensor didn't work for whatever reason. There's a backup in there that says, hey, your sensor doesn't work, so I'm going to back off 100% of the time and effectively cripple the transmit power until to safe levels. So, and what the user will detect that in terms of, you know, user experience will be dropped heavily because of that. Yeah.
The final question from Ian Simpson: if tablets are too big, could you use balanced antennas rather than ground planes to double the size of everything? I'm not sure I quite follow that, but anyway.
Yeah, I mean, probably too big. I think a balanced antenna is usually pretty big. There's just no room. That's the reason why you have very small antennas with big screens there. It's because we are using the ground plane as effectively the radiating element. That is the radiating element to be honest. It's not the little antenna at the top. That's just an exciting element. So yeah,
Okay.
there's been looking for a long time, but yeah, it's never really called because of the size problem. Yeah.
Just a question for myself on SAR.
Yeah.
So the SAR limits in the UK for amateur radio people are actually integrated over a 6-minute length of time.
Oh, yeah.
Which is time taken into account for US?
So what I've showed you today was sensors, physical sensors that we've been using for many years. So one of the innovations that we've moved to is averaging SAR. So we now don't have physical sensors. We actually have a moving average filter monitoring the transmission. So our new devices don't have any sensor at all. We're actually monitoring the transmit portion of the signal and averaging that over, depends on the frequency. So if it's the lower frequency, it's probably about a 30-second window. And then if it's a higher frequency, it's like 2 gigahertz, it's probably like a 10-second window. But yeah, we have actually now our SAR averaging. So that's something that we're actually using at the moment.
Okay, right.
Yeah.
Well, Mark, now's the time to pull the plug, so to speak. Thank you so much for a really interesting comment. Now, there's been quite a few other comments which have come in, which are to thank you and praise you and all the rest of it. And I want to give my personal thanks and also thanks on behalf of the Sussex IAT for a really interesting talks, and the comments are still coming in. So what we'll do is we'll close this now, but
Yep.
to leave it for a minute or so just for any final comments, which you yourself can have a look on the either the chat or the Q&A. It's coming in on the chat at the moment. So thank you, Mark. I'm going to switch off and wait for a couple of minutes, and see you again sometime.
Yeah, thank you for inviting me to this. It's been awesome. It's nice to connect with the UK again. It's been a while since the COVID, because I haven't been home. I usually visit home, like once a year, but I haven't been because of COVID. So yeah, nice to hear old voices.
Okay, bye then.
Take care. Bye bye.